So now let's continue with substitution reaction, which is particularly we were talking about SN2 reaction. So now in SN2 reaction, if we see, we have next reaction is Finkelstein reaction, or which particularly known as halide exchange reaction. So in halide exchange reaction, we have a halogen which is replacing the second halogen. This particular reaction is Finkelstein, and which is proceeding in the solvent of acetone. So acetone, it is a non-polar, it is polar aprotic. It is a polar aprotic type of solvent. Now we know that iodine is again we know when it is a polar aprotic, and enhance the SN2 mechanism. We will see further while discussing, before discussing the SN1 mechanism, what is the nucleophilicity and how it is increased. So here we know that nucleophilicity increased because the intensity of I minus increased. When nucleophilicity is increased, it is moving towards its bimolecular. It is making it more moving towards the second order, and when it is second order, we know it's a SN2 mechanism. So here iodine, it is following SN2 mechanism, it is replacing bromine. So as the remaining are Na, Br. So this is a precipitation is forming, and there is a exchange of halogen. So now jumps to example. If we have this particular example and we have sodium iodide in acetone. Now sodium iodide, we know that this iodine is going to replace bromine with the help of SN2 mechanism. SN2 mechanism, we know there is a inversion in configuration. So when we talk about inversion, we know that iodide is not going to replace bromine, but it has replaced the bromine here. But is it the correct answer? We know it is not the correct answer, because there should be also an inversion. Inversion should also be there. So when we talk about inversion, we know that there is a change in configuration from R to S or S to R, but here there is no change in configuration. So either we convert that we know it is a Fisher projection. Here it is a Fisher projection. Whether we convert from Fisher to wedge dash, and then again wedge dash to Fisher. Okay, so in that we could do, or what we could do, we can simply change the configuration of this structure, and we can replace bromine by iodine. So we could try to figure out its configuration. We know this bromine is 1, ethyl is 2, and methyl is 3. So it is going like this 1, 2, 3. So it should be R, but hydrogen is on vertical. It should be on horizontal. Okay, it is on vertical. Okay, so now here 1, 2, 3, it is R. So the configuration here it is S. Now we check the configuration here, it is 1, 2 and 3 again. So it should be S, but it is R. Okay, because hydrogen should be there. So we know, and these two are identical. So what we could do in case of SN2 mechanism, either change Fisher to wedge dash and wedge dash to Fisher again, or we could change the configuration and replace the molecule by its own substituent. Now if we see here NaI in acetone, again we know it is promoting the SN2 mechanism, and we have two halogen which could be replaced, fluorine and bromine, and we know that the bromine has a more leaving tendency. The leaving power of bromine is more, that we have seen over previously in case of SN2 mechanism. So hydrogen, fluorine, and here we know there will be iodine and hydrogen. So this bromine is going to replace. Again, if we talk about here we could replace only bromine. So when we could replace only bromine, we know this is its axial position. Now that when it replaces from backside, it comes in equatorial position. So SPH is on equatorial position, and it is 1, 2 and 3. So this group is retained by itself. Now these two more examples we have. I'll again promote you, I'll again encourage you to pause this video once and try to answer by your own. Now in this reaction, if we try to replace that iodine with SH, then that will be wrong, because we have replaced the iodine, but we have not changed the configuration. So we know when we exchange this loop once time, so its configuration gets changed. We know only this carbon gonna affected by SN2 mechanism, and this the configuration is not gonna affect by SN2 mechanism. So we know that here if we exchange this loop by once, we are changing the configuration. When we are changing the configuration, now we could easily D H H or D and methyl group. Now here if we apply SH, there will be the correct answer. Now if we know there are two positions, then equatorial and axial. So PHS will be attack over there, S minus is acting as a nucleophile, and the bromine is a living group here. So in this reaction we know that is not going to participate because that is not a living group. A good acid is always a living group. So here we know that the SH will attack from over here, and it will be SPH, and it will be like 1, 2 and 3. It will be gonna make 1, 2 and 3. So these are all types of product we get in the reaction of Finkelstein reaction. Again, one more reaction if we talk about, it is a Williamson ether synthesis. Okay, Williamson ether synthesis. Now we know that this is this is alkoxide. Okay, this particularly is known as alkoxide, and this is we know alkyl halide, and this is alkyl halide. When we know that should not be 3 degree, then R dash should not be 3 degree. We know because this follows SN2 mechanism, and in the R or the condition of hormone could be methyl 1 degree and 2 degree, but it should not be 3 degree. This is the condition. We will see later when it is 3 degree, it's gonna go by elimination reaction. But here we haven't seen. So we know that when it is 3 degree, it is making happen towards the elimination reaction. So alkene formation will be there. So when we want to proceed the SN2 mechanism, when we want specifically the Williamson ether synthesis, then we should not make the R dash equals to 3. So there is a formation of ether, and this salt will form. Okay. So in Williamson alkoxide react with alkyl halide by SN2 mechanisms to form ether. So these are examples. Now we know that this is a methoxide. Okay, methoxide gonna replace here. This is all we know. This is methyl. So easily it's gonna form SN2 mechanism. So it is OCH3 ethoxide C2H5. This type of ether will be there. Isopropoxide OCH3. Tertiary butyl oxide, again SN2 mechanism, it will form CH3. So all gonna replace bromine because there is no hindrance in forming SN2 mechanism because it is methyl, easily accessible to SN2 reaction. Now guess the reactant. Again, if you see the reaction, guess the reactant of Williamson from a given product. So we have given product. Now we have to identify the reactant. So when we need to identify the reactant, so we know there are two cases. It could be CH3Br, and this should be alkoxide, or we know it is this type of bromide, and it is CH3O minus. So we know that this could easily SN2 mechanism. So this is our correct answer. Okay, and this is all not correct answer. So means preferable answer. Okay, so it is our more preferable answer because it is easily SN2 mechanism. Now if we talk about this, it is CH. Okay, it is, if we categorize it, it is PHCl plus CH3O minus, or we can talk about PHO minus plus CH3Cl or Br, any alkyl halide. So we know that whether this alkoxide ion is not much intensify, it is more stable, but it is still the formation of this product is more from here, less from here, because we know that chlorine cannot be replaced, but we have already seen that doesn't give SN2 mechanism in that aryl halide. Now if we see the third reaction, so in the third reaction, if you see that it is forming O minus, and it is CH2 3SC CH2 Br. So this is more preferable because we know that when there will be chlorine, it will be 2nd degree, but here it is 1 degree, so it is more preferable. We know this will not proceed towards that Williamson ether synthesis. And this is also not be formed by Williamson ether synthesis, because here in both the case you will see resonance. Okay, here also if we talk about the PHBr, and it is a CH, 2 double bond CH and O minus. In both the case it will be not proceeding through Williamson ether synthesis. If we talk about this particular PHO minus plus this 3 degree and bromine is here, or we talk about it is O minus plus PHBr. In both the case we know 3 degree don't give the SN2 mechanism, and here we know phenyl as resonance stabilized, but also don't give SN2 mechanism. So it is also not possible to form a Williamson ether synthesis. Now if we see that reaction, in the next reaction we know there are two types of products, CaO and CH3Br, or we can say it as or it is CH3O minus plus this 3 degree bromide. So we know here the reaction could take place, and here now here if you go toward both the reaction, here the product will be this. Okay, here if you see this will be our product, but here if we try to proceed the reaction, we know that it is 3 degree. We know when it could be 2 degree, 1 degree or methyl, it will form SN2 reaction. But what if we have a 3 degree? We know there is a elimination reaction. In that case the product will be elimination product. So in that case this bromine will leave and this hydrogen will be there, so that product will be elimination product. So here it is elimination product. So now if you see this reaction, we know NaNH2 it is a base and it is an acid. So we know the fastest reaction in the world is the one of the fastest reaction is among the ionic reaction. It is acid base reaction. It could be ionic reaction or it could be acid base. So A will be simply a base, CH3 C triple bond C minus. So it is a base, and we know base are nucleophile, they have negative charge. Now it is again an SN2 mechanism. So we know when there is a nucleophile and we have any 1 degree methyl alkyl halide, so we know easily it will be going SN2 mechanism. So it is C double bond C and CH3. Again if we talk about this, it will be PH C triple bond C minus. So it will go to replace iodide here. So it will form PH C triple bond C and ethyl. So these reactions are known as step up of alkyne. These are categorized as step up of alkyne. So here we are stepping up the alkyne by making a nucleophile and making it substitution reaction towards the mechanism of SN2.